Yeah, thanks. Yeah, first of all, I would like to thank the organizers for gathering us together in this wonderful place and giving me the opportunity to talk here. And well, indeed, when I was thinking what to talk about here, well, one possibility was to talk about using modularity for calculation of some BPS indices on Calabi-Yau threefolds. But then I thought that, well, maybe half of people doing resurgence will be bored. So I tried to find some topic which would involve both modularity and resurgence. And well, finally, I decided to talk about, well, some old problem, which I believe probably can be solved if one uses these two magic tools. So both modularity and resurgence. And this is what I would like to explain you during this talk, how modularity and resurgence enter this problem. And although the problem is old, well, probably with the new techniques of resurgence, which were developed during last years, maybe now it will become doable. So let me first explain the setup. So what I'll be talking about. So let's consider some type 2 string theory. It can be type 2A and type 2B, and compactify it on some Calabi-Yau threefold. And well, then we know that we get in 4D n equal to supergravity. And I'm interested in the effective action of this supergravity at the 2 derivative level. So effective action at 2 derivative level. And actually, we know very well that at this level, the effective action is completely fixed by the metric on the modular space of this theory. And the modular space, in fact, is a direct product of the vector multiplet modular space and hypermultiplet modular space. So, in other words, there are these two manifolds. I will just mention a few facts about them. And if we know the metrics on these manifolds, we can write explicitly the effective action at this 2 derivative level. So what do we know about these manifolds? Well, about this we know essentially everything, because first of all, this is known to be the special Keller manifold, which means that the metric on this manifold is completely captured, not just Keller potential, but a holomorphic function, which is called holomorphic prepotential. F holomorphic prepotential. And it's classically, well, it's 3-level exact because there are no GS corrections. And we know, well, we can compute this prepotential and hence the metric on this manifold explicitly. Well, for example, in type 2B, F is just the prepotential, so it's prepotential on the complex structure modular space of Calabi-Yau. And if we are in type 2A, F is prepotential on the Keller structure modular space of Calabi-Yau. So, and then, of course, there is this famous mirror symmetry, which exchanges them if we map Calabi-Yau to its mirror. And for example, yeah, so there I already wrote down an explicit formula for F in this case. And so we see how it looks like. So it has essentially 3 pieces. So the first piece is just classical. So it's a classical contribution, which you can derive just by doing Kaluza-Klein reduction on Calabi-Yau. Then there is a contribution from perturbative alpha prime correction. And then the third contribution is the contribution of wall sheet instantons, where this coefficients nk of 0. These are genus 0 Gopakumar-Waffe invariants of the Calabi-Yau. And this is a tree logarithm which takes into account the multi-coverings of worldsheet instantons. So this is alpha prime perturbative correction. This is worldsheet instantons. So this is all what we need to know about the vector multiplet modular space now. And what about the hypermultiplet modular space? This guy is actually much more complicated. So the first fact, which already complicates a lot, that this is the so-called quaternion Kähler manifold. So this is just requirement of n equal 2 supersymmetry in 4D. Quaternion Kähler. This is a quite complicated type of geometry. It's even more complicated than hyperkähler geometry. For example, it's not even Kähler manifold, so the name is somewhat misleading. It's not even a complex manifold. There are just almost complex structures, more precisely 3 almost complex structures which form a quaternionic structure on it. Well, but still, well, somehow this imposes quite serious restrictions on the metric. And from the physics point of view, most important fact that there are GS corrections, both perturbative and non-perturbative. And the current status is that we do not know the full metric on this guy, and hence we do not know completely our effective action even at the 2 derivative level. And well, this is kind of the general formulation of the problem which I would like to consider, namely, can we get the full non-perturbative metric on this modular space? But let's now be more specific. So what we know and what we don't know about it. So let's go step by step. So first, well, classical metric. Classical metric is actually well known. So it's given by the so-called C-map. So this is a certain procedure which allows to construct a quaternion Kähler manifold in a canonical way out of a special Kähler manifold. So it's also completely determined by the prepotential, but the mirror one. For example, if we are in type 2A, let's say, so vector multiplet modular space is determined by the prepotential on the Kähler structure modular space of the Calabi-Yau, then the hypermultiplet modular space at classical level will be completely determined by the prepotential on the complex structure modular space. So they kind of mirror to each other in this sense. And so it means that at classical level we know the metric well explicitly. Actually I will just in a minute I will show you the formula. But before that, let me also say what happens at the perturbative level. So perturbative in GS, what I mean. And at perturbative level, remarkably, there is just one loop correction and nothing more. Already here, you could ask what kind of resurgence I will mention. Well, you will see the resurgence will be very unusual, which I will talk about. So we have just one loop correction. So and we know the metric explicitly. So I wrote it in advance because otherwise it would take a lot of time just writing it. But it's just to flash you the result. So it was obtained, well, in 2007 in one of my papers. And so this is just to well, flash the result, explain the notations, and mention one open problem in this story. So this is how it looks like. So these are the fields. So they are coordinates on this hypermultiplet modular space or fields in 4 dimensions from the target space point of view. So there are complex structure. So we're in type 2A. So I wrote this formula for type 2A. So these are Z's are complex structure moduli of the Calabi-Yau. Zeta and zeta tilde are Ramon scalars, which are obtained by periods of the type 2A3 form along 3 cycles of the Calabi-Yau. Then R denotes exponential of the dilaton. So it's like 1 over GS squared. And then sigma is the dual to the B field. So it's an S axion. So, and then what else? K is the Keller potential on this complex structure modular space. This is the, well, probably familiar for some of you, is the matrix which multiplies, which encodes the couplings of the gauge fields. It also appears here. And then there is, well, some non-trivial connection for the NS axion. And the most importantly, so you see that this metric depends on a parameter C, which is just a number determined by the Euler characteristic of the Calabi-Yau, and it is this parameter which encodes the one loop correction. So if you put it to 0, you reproduce the classical C-map metric. Otherwise, it's well, this non-vanishing number. And you see that there is actually a problem that, well, R is of course positive, but C can be both negative and positive. In particular, if we consider rigid Calabi-Yau for which h to 1 is equal to 0, chi is always positive, so C is always negative. And then this metric has, well, it looks like there are 2 singularities at R equal minus C and at R equal minus 2C. One can actually show that the first singularity is just coordinate singularity, so it's not a problem. But this is really curvature singularity. And from the physics point of view, the modular space cannot have such singularities. So this singularity must be resolved somehow. Of course, the hope is that it's resolved maybe by instanton corrections. But it's still an open problem how it happens. It was not shown that it is indeed resolved, and it's not known how it happens. So there is, you see, there is even a huge open problem, even at this very, very basic level. There is no physical reason for them, for this to happen somehow. You see, it's just for some particular value of the dilaton. Yeah, of course, once you include, yeah, yeah, of course, when you include some instanton corrections, the position of singularity a little bit changes, but still, well, it's some strange curvature singularities which doesn't have any physical explanation. Well, something should be explained here. Okay, so this is all about perturbative metrics. So what about non-perturbative? Non-perturbative in GS. And there are 2 types of instanton corrections which contribute to the metric on this hypermultiplet modular space. So let me start from the first type, which are d-instantons. So d-instantons, they come from dp branes wrapped on some p+1 dimensional cycles. So these are Euclidean branes whose walled volume is completely wrapped. And just on general ground, it's known that they expect it to behave like exponential minus, well, instanton action, which in our case looks like that. So where z gamma is the so-called central charge. So we can write it like this, minus p lambda f lambda of z. So these are our complex structure moduli, and q lambda and p lambda, they form electromagnetic charge which labels different instantons. So essentially it labels just the cycle which your deep brain is wrapping. For example, in type 2A, this will be D2 brains which have three-dimensional world volume, and gamma labels different 3 cycles which are wrapped by the D brain. And it's also important that here we have these instantons are weighted by numbers, which are, from the physics point of view, they correspond to BPS indices. And from the mathematical point of view, they coincide with the so-called generalized Donaldson-Thomas invariance, which mathematicians are really very interested in, but it's very difficult to compute them for compact Calabi-Yaus. Okay, now let me make a small table just to show you which kind of D-brains contribute to the story. So let's put here type 2A, type 2B, and let here put dimension of the cycle, which will be wrapped by, and this is D brain. And here we also have D cycle, D brain. And then which kind of D brains we have in type 2A? Well, of course, D0, D2, and D4. Well, we shouldn't include D6 because D6 has 7-dimensional world volume, so of course you can wrap it on the whole Calabi-Yau, but then some dimension will remain. So we shouldn't have any dimensions along our non-compact Minkowski space. So this should wrap 1-dimensional cycle, this 3, this should wrap 5-dimensional cycle. But on Calabi-Yau, there are no 1-dimensional cycles and 5-dimensional cycles. So these D brains, they do not contribute to the story, and we remain just with contributions of D2 brains. And in type 2B, the story is completely different. We have 4 types of D brains, and all of them contribute to the story. And actually, on type 2B, it will be convenient to decompose the electromagnetic charge, so we can write it like P0, Pi, Qi, Q0. So essentially, we just decompose the index. So before we had, so here we have like gamma P lambda Q lambda. So kind of decompose lambda into 0I. And then this component will, under mirror symmetry, so this component will correspond to label D5 brains. This will label D3 brains, this D1 brains, and this corresponds to D-1 brains. And what is the situation about these D-instanton corrections to the hypermultiplet metric? Actually, we know them exactly. So we, well, about 15 years ago, we computed them. Well, first, they were incorporated using the so-called twistorial description of these manifolds, because actually the most efficient way to work with quaternion Keller geometry is using some twistor spaces. I don't have time to explain how it works, but, well, believe me, this is the most efficient mathematical description of such type of geometries. And these guys precisely were in the beginning incorporated in this twistorial approach, but then it takes quite a lot of work actually to extract the actual metric out of this twistorial description. But this also has been done. So in other words, we know these guys explicitly. Although there is a little caution here, because we know them in type 2A. So what about type 2B? Well, you can say, of course, just apply mirror symmetry, because you know, type 2A on one Calabi-Yau is the same as type 2B on another Calabi-Yau. But there is a problem here, because if you want to rewrite, I recall that in type 2B, we have S duality, yeah? we have S-duality. And the natural fields in type 2b, they transform nicely under S-duality. And if you want to rewrite the metric in terms of these physical type 2b fields, you have to apply what is called mirror map. So it's kind of coordinate transformation from type 2a fields to type 2b ones. But this mirror map also gets all possible perturbative and non-perturbative corrections. And you have to find them. Sometimes it's possible, but generically it's complicated. So yeah, so one can say that, yeah, in principle we know the metric on type 2b, but in the natural type 2b coordinates, well, not completely. Okay, so this is well, what I mean that I know the metric parameterized by these guys. So these enter as a parameters. Yeah, and then to get the actual numbers, I need these numbers here. Yeah, yeah, yeah. And okay, so this is the first type of instantons, and this is not the end of the story, because there is the second type of instantons, namely NS5 instantons, which come from NS5 brane, which has 6-dimensional world volume, and you can wrap it on the whole Calabi-Yau. And we know that these guys, they behave, well, roughly like 2 pi some instanton number, let's say k, then the volume of the Calabi-Yau divided by GS squared. So you see the behavior is very different from the instantons. This is like 1 over GS in the instanton action. This is 1 over GS squared. And these guys are really complicated. So in a sense, by the way, yeah, I forgot to mention that this twistorial description of the instantons is very similar to, if you, some of you know, the construction due to Gayota, Moore, and Neitzke of instantons in n equal to 4-dimensional gauge theory compactified on a circle. So these guys, they in this case, in 3 dimensions, there is also effective action corrected by instantons. So these guys, they provided twistorial description of the corresponding modular space in 3 dimensions. So the construction is very, very similar to their construction. Just the difference is that they have hyperkähler modular space. In our case, it's quaternion Kähler. But otherwise, the construction is almost the same. So in other words, these D instantons, you can think that they have kind of gauge theory analog. So you can find something similar in gauge theory. Whereas, well, at least I don't know anything similar to NS5 brane instantons. So it's really, for me, it's pure stringy effect. And this is why it's much more complicated. And it is these guys which we do not know. Well, we know something about them, which I will tell you. But it is these guys which are not known. And I believe it is to find these guys, we should use a combination of modularity and resurgence. And in the rest of the talk, I will actually want to argue why it is so, why I believe that modularity and resurgence can help us. And so this will be the main message of my talk in the following. So let me remove this. Okay, let me leave this for a moment. So let's start first of all from modularity. So how modularity enters the game? Well, I already mentioned that we know that in type, it's known that in type 2b, string theory, we have S-duality. or more precisely, we actually have the full SL to Z duality group. And the first question, how, this is the duality symmetry in dimensions. So how it is reflected in the effective four-dimensional theory? The answer to this question is very simple. So this must be isometry. This must act as an isometry of this hypermultiplet modular space. So we have this additional restriction on our metric that it must be an isometry. So I already told you that, well, some part of the metric we do know. So what about this restriction? Is it consistent with what we know? So let me now tell you about this. Let's consider the so-called large volume limit. Large volume limit just means that I take the Keller moduli of my Calabi-Yau, let's call them Ti, and I consider them very large. So these are Keller moduli. And then this limit, it turns out that there is all quantum corrections kind of form a hierarchy. So first, so there will be 5 levels of this hierarchy. So first, there will be classical metric, of course. But classical here, I mean that I ignore both GS corrections and alpha prime corrections. So it's obtained from this metric by putting C equal to 0 and also taking for the prepotential just this first classical piece. So just substitute in that metric this F, but just the first term. And then it's straightforward to check that the resulting metric, it is invariant under SL2Z. Actually, even better, it is invariant under SL2R. So just one can check this explicitly. And now, what I want to say by saying that there is a hierarchy of corrections, of quantum corrections here, is that each level must be separately invariant under SL2Z. So they form kind of different orbits under SL2Z. So there will be different orbits like this. So in other words, not only the whole metric is invariant, but kind of the classical metric is invariant, then the some type of corrections is invariant, another type of corrections is invariant, so on. So they are not, different orbits are not mixed under the action of SL2Z. And so the first non-trivial orbit, which appears here, corresponds to perturbative alpha prime, GS, and D-1 instantons. In fact, this is how D-1 instantons have been found. So the people just started from alpha prime and GS corrections, perturbative these corrections, and imposed the SL2Z symmetry. And it turned out to be sufficient to derive D-1 instantons. Well, you know this in the context of string amplitudes, so we heard about this several times during this conference, but the same strategy works for this hypermultiplet modular space. Here it's a bit more complicated because you work not with a single function, you work with the whole metric tensor. But again, if you use this twistorial description, which I mentioned, then it's kind of essentially a problem to a certain set of functions. Okay, so okay, so these guys, so yeah, I told you there will be different orbits and they scale differently. So you can say that this is like scales like 1, this is like e to minus t, this is like e to minus t squared, and there will be the last orbit scaling like this. So you see they cannot mix because they have different scaling in this large volume limit. Now, the next orbit is corresponds to wall-sheet instantons and D1 instantons. So again, you can start with, and again, this is how D1 instantons have been derived. So you can start by including wall-sheet instantons, just using this formula for the prepotential, and then you can derive D1 instantons by imposing SL to Z. Or also, we heard yesterday, so this corresponds also to PQ strings. So another name for these guys in type 2B. Well, you can already guess what will be the next sector. The next sector will be corresponds to D3 instantons. And actually, from the point of view of modularity, this is the most interesting sector. Because you see, comparing to the other two sectors, D3 instantons are S-duality invariant. They're not mixed with other branes or anything, or perturbative corrections. And this is a very non-trivial. The point is that I told you, D instantons have been derived in type 2A formulation. You can map them using mirror symmetry to type 2B, and by some miracle, they should turn out to be SL to Z invariant. Well, in this sector. And this is really non-trivial. So this is actually, again, for people doing modularity, this is like Klondike, I don't know, like the place where you can find a lot of beautiful modular, mock modular functions, high depth mock modular functions. So this is a really beautiful place. Well, since I think I have some time, so let me tell you a little bit more about this sector, because it's really beautiful. So what happens here? I told you, by some miracle, these guys should respect SL to Z symmetry. And actually, how to say, the point, what happens is that they do respect this symmetry. It's very non-trivial, but this happens. But this imposes certain restrictions on these BPS numbers. So in other words, what happens is that for arbitrary BPS indices, you do not have SL to Z. You have them only for some special sets of values. And which sets? Namely, what happens, one can derive, and this is really non-trivial, one can derive restrictions on modular properties of BPS indices corresponding to D3, D1, D-1 bound states. Or again, you can map them to D4, D2, D0 black holes in type 2A. And mathematically, they correspond to the so-called rank 0 Donaldson-Thomas invariance. So what happens, you form generating functions of these guys. So they will be generating functions labeled by some of the charges, for example, this pi. And they will be functions of the modular variable tau. And so they are constructed, roughly speaking, like some over certain charge n omega of n q to n, yeah? And where these omegas are essentially these ones. And what happens that these guys should have some modular behavior. And more precisely, it turns out that if P, this charge, so it corresponds to some 4 cycle on the Calabi-Yau, yeah? Because it's wrapped by D3 brane. So if this cycle is irreducible, so it cannot be decomposed as a sum of other cycles, then this turns out to be a modular function. And if it is reducible, it turns out to be mock modular. And the essential degree of reducibility determines the depth of mock modularity. And there is a precise modular anomaly which one can derive. So in particular, what means the precise form of the shadow of mock model functions. And this can be actually used to find these guys. So this is how we recently found these DT invariants for some compact Calabi-Yaus. So one can use these modularity properties to actually find the whole generating functions. So this is really non-trivial restriction. And also, one can, for example, take also the limit where the Calabi-Yau becomes non-compact and relate this to some topological theories or some gauge theories. For example, this has also been used to derive some results for Waffa-Witten theory. So one can derive also generating functions of Waffa-Witten invariants out of this modular constraint. But this is very rich sector, yeah, and interesting for people doing modularity. But actually, the sector which we are really interested in is the other one, where we have D5 instantons and also NS5 instantons. And well, we know from physics that actually S duality maps one to another. Yeah. It maps D5s to NS5s and vice versa. And now, well, there is a natural question. Can then maybe we use this S duality to derive NS5 instantons from D5 ones? Because I told you, well, in principle, we know all the instanton corrections. So can maybe we use S duality to get NS5 corrections? Of course, this idea was very old, and there was an attempt to do it. And so let me now very briefly describe what one gets. And you will see that, one can obtain some results, but they're incomplete. So the problem is not, so as I will argue, just using S duality is not enough to solve this problem of NS5 instantons. I told you that the most efficient way to describe the instantons is using twistorial description. I don't have time to explain you, but let me explain just one simple thing, that the end point of the construction is the following, that the whole metric in this twistorial approach can be derived using, from just two sets of data. So we need two sets of data. So first of all, we need to draw some contours on CP1. So we have certain, Riemann sphere, yeah, and we want to draw some contours on this sphere. I know, so for example, there will be one around the North Pole. I will tell you later what they are. So what is this sphere? This is precisely the sphere of which appears in twistor spaces. So what is twistor space? Twistor space is just CP1 bundle over the original manifold. So, and geometrically it describes this triplet of almost complex structures. And so it plays so everything interesting happens on this twistorial sphere. And so my claim is that let's consider some contours on this CP1, and then associate with each contour holomorphic function. Holomorphic function. Holomorphic in the sense of the twistor space. So the twistor space, in contrast to the original manifold, is a complex manifold. And one can introduce some sets of holomorphic coordinates. I will call them psi lambda, psi tilde lambda, and alpha. And well, essentially, we need to introduce functions of these three guys. So just let me give you an example. For example, how do I get the classical metric, which I already erased? In a very simple way. So I just draw two contours, one around the North Pole and one around the South Pole. Yeah. So there will be two contours, and to this contour, I attach the holomorphic function f of xi, and to this one, f bar of xi. And I claim just from this data, I can derive my classical metric. I don't have time to explain you the procedure, how it's done. It's actually a very non-trivial procedure, but well, it's very concrete. So the first step will be to get twistor lines out of these functions. This is kind of the first step of the construction. So by twistor lines, I mean, so what I need to compute essentially, I need to compute these guys as functions of my coordinates on my original space and the coordinate on this sphere. So I will call it T. So T will be coordinate on CP1. So this is the first step, but it can the data which encode the most fundamental data are these ones. They're kind of, this is like having prepotential for special Kähler manifold. But the difference is here is that there is no single prepotential. There are several prepotentials, and they're associated to some different contours on CP1. So that's the difference. And now, so this is the classical metric. How do I introduce the instantons? Again, very simple. I draw contours which will be rays from north to south pole. So to each charge gamma, I attach such a ray. And essentially, my central charge, Z gamma, indicates kind of in which direction I should draw it, here or there. So it's determined by the central charge. And the holomorphic function in this case will be a function of xi and xi tilde, and it's given by this omega of gamma by, well, 2 pi squared times dilogarithm. Dilogarithm, well, let me write. Of what? Of just exponential 2 pi I of q lambda xi lambda minus p lambda xi tilde lambda, where q lambda and xi lambda, I remind you, this is my electromagnetic charge, gamma. So this is, and my claim is that just from this function, one can derive the whole d-instanton corrected metric, which is a huge, huge metric, but it just follows from this simple function. And now, what about S-duality? Actually, we also know how S-duality acts on the twistor space. So, for example, we know that on these twistorial coordinates, it acts in a holomorphic way. So we know how they are mapped, and actually you will see the maps are very nice. So, for example, let's take psi 0. So I split my lambda into 0 and A coordinates. So psi 0, well, you immediately recognize, yeah? It transforms like a modular parameter. And psi A transforms like an elliptic variable. And psi tilde A is, well, essentially is, well, it's not completely invariant, but almost. Kappa ABC, psi B, psi C, where kappa ABC are intersection numbers of the Calabi-Yau. And finally, psi tilde and 0 and alpha, they transform like a doublet. D minus C minus B C, psi tilde 0 alpha, plus some nonlinear terms, which I will not write. Yeah, sorry, I was a little bit inconsistent. Typically, I use A in type 2A and I in type 2B, but yeah, so if you wish, just replace by I. Yeah, so it's, well, it's when you use mirror symmetry, well, you map one to another. Yeah. So in fact, there is such a fact that each type of coordinates is associated with one types of instanton correction. So you can think about psi 0 like associated to d minus 1 instantons, psi a to d1 instantons, psi tilde a to d3 instantons, and you see that it's almost invariant. And psi tilde 0 to d5 instantons and alpha to ns5 instantons. And you see that these guys transform to each other. So like ns5 branes transform to d5 branes and vice versa. And now, we also know how this coordinate t transforms. So t, well, essentially it transforms to by some fractional linear transformation. So there will be some, well, I don't write explicit formula, but essentially it's kind of certain fractional linear transformation. So we know how it transforms. And so then the idea is very simple. Let's just take these transition functions. So this, yeah, I call them transition functions. So these holomorphic functions encoding d instantons. So let's take one for where there is non-vanishing d-fibrine charge. So let's say p0. And let's just apply this transformation, so S duality transformation to this function and to this contour and see what we get. So what do we get then? We get a little bit strange picture. So let me now, just for the sake of simplicity, let me map this sphere to the just plane by stereographic projection. Yeah, so I have a complex plane. So these are my axes. So then d instantons, they correspond to contours like this somehow. And then if I map them under S duality, what happens is then that I find contours something like that going on. So something strange. And I can also derive the corresponding functions. So S acting on H gamma. So let me call them HK gamma, where K is the NS fibrine charge. So I can get the explicit form of these guys. And well, at one instanton level, so if I work in the one instanton approximation, in principle, there is no problem. Even recently with my PhD student in last September, in a paper, we computed the one instanton corrected metric out of these functions and obtained some results which, well, at least by its general form, consistent with what one expects from stringy amplitudes. What I mean is the following, that we obtain the metric, so ds-ns5, which has the following interesting form. So there is an instanton action here. So this is for some k gamma. And then in the limit of small string coupling, so this metric can be written, it's very non-trivial. What happens, it can be written like, well, it's a square of a one form up to the differential of the instanton action. So this is one form, this is one form, this is one form. So this guy is a two form. Yeah? And precisely this form of the metric in this limit follows by considering the structure of stringy amplitudes. And so, in fact, we derived predictions for stringy amplitudes in the presence of NS5 branes. And most important, there is this consistency check. But on the other hand, so this is if one works in the one instanton approximation. But the problem arises if one wants to compute like two instanton corrections and so on. Why? Because this picture is completely ridiculous. it doesn't have any sense. Why? Because you see, these contours start intersecting. So there are these points of intersection here and there, and it doesn't make any sense from the mathematical point of view. Because, well, it would mean that there is some non-trivial monodromy if you go around this point, but these points are not even fixed on the complex plane. Because in principle, you should be able to deform all these contours. So it doesn't have any sense. So this construction, it works only at the one instanton level where you can ignore all these intersections. But at multi-instanton level, it's completely nonsense. And therefore, and this is why I claim that S-duality is not sufficient to get NS5 brane corrections, because it leads to some meaningless picture. But now, in the last 5-10 minutes, so what about resurgence? So I promised to you that there will be some resurgence, and indeed, so this is so here I would like to make a comment which is based on a paper from 09 by Pulin and Van Doren. So they noticed very interesting fact. So we have these d-instanton corrections, which I discussed. And you remember the d-instanton corrections had been weighted by this omega, and they had instanton action, which was like z gamma modulus by gs. Yeah, maybe 2 pi here, yeah, doesn't matter. And this is typical form of d-instanton corrections. But of course, you must sum over all charges, yeah? But I told you, so these guys, they are BPS indices, and we actually know also that, well, under some dualities, they also correspond to degeneracies of BPS black holes. But we know how entropy of BPS black holes behaves at large charges, yeah? So they are proportional to like exponential of, well, essentially gamma squared. Well, if one defines what it means by square of this charge. But, well, roughly speaking, it scales like quadratic in the charge, and it exponentially increasing. Whereas this is only linear in the charge, yeah? So we get something like exponential of gamma squared minus something like this, yeah? So it is this sum over charges that horribly diverges. And then, well, already here you can easily guess what happens. Now let's evaluate kind of the ambiguity in this series by the usual methods. And well, for this essentially it's enough to extremize in gamma, yeah? And you see that the ambiguity which comes from here is, well, essentially it's proportional, something like 1 over gs squared. So in other words, what one finds is that the ambiguity of the asymptotic series over charges, which follows from the d-instanton corrections, behaves like NS5 instantons. So there is this additional, very non-trivial relation between d-instantons and NS5 instantons, which relies on this on the resummation of this asymptotic series over charges. And now the question which I would like to ask, whether one can use both constraints from S-duality, combine them with this observation about resummation of the sum of charges, and finally get something meaningful and complete results for NS5 brane instantons. And let me also mention that, well, of course, in our problem, there is no, so the instantons, they do not arise due to some Borel resummation. Yeah, like it happens very often. Because in our story, you remember, there was no perturbative series. There was just one loop correction and nothing else, no other perturbative corrections. But in some other contexts, the instantons do arise well, due to some Borel resummation. For example, we know in topological string theory, one can get corrections due to Borel resummation which do behave like the instantons. And they do have Stokes constants given by these BPS indices. So this is what Marcos Marini, for example, is arguing all the time, yeah? That he finds Stokes constants appearing in topological strings, and which coincide with these Donaldson-Thomas invariants, so with these BPS indices. So from this point of view, then what happens? And you know, so this, then the instantons, they arise like singularities in a Borel plane, yeah? And the typical, structure of these singularities is like that. Yeah, actually it resembles this BPS rays which encode these d-instanton corrections in the twistorial picture. So one can also ask whether there is some relation between these two planes. But let's forget this for the moment. What I want to say, most importantly, is that here, so they correspond to different charges, so they are labeled by charge, all the singularities, and you can think that if you go in this direction, so the charge increases, and then, so it looks like I suggest a kind of a new resummation which might arise, maybe in some theories, that you see that this resummation of a charge, of the series of charges, would correspond to the resummation of a sum of different singularities in the Borel plane. So especially when you have, when they have this ray structure. And so it would be interesting to see whether in some theories this leads, such sums, they lead to some divergent series, and what is the interpretation of the corresponding divergence, because it looks like in our case it should correspond to precisely our NS5 branes. So yeah, so this was my main message, and thanks for your attention. So you do have some asymptotic series out of such. It's a question, or I don't know, because I didn't study this problem really. So just I thought it would be interesting to present it here. This is, I think, the right audience for solving such kind of issues. What do you mean? Well, of course, if you here, for example, you restrict to this sector and take the limit of small gs, you will remain just with d5. Yeah, no NS5. But I don't know what you want precisely. Well, I don't know. I don't know. I didn't think about this, but I don't see how you would get it precisely. Because if you take also, if you take GS finite and just consider the large volume, well, there is this hierarchy, but it's unlikely that you can think about them as different levels of free summation. Yeah. So in this limit, there is just one. One can say there is just one type at each SL to Z invariant orbit. So it's like having PQ strings or PQ5 brains. So yeah, I'm not sure what kind of other limit one can invent. Yeah, this is not really a correction. It's already appears at classical level because the C is ABCD of SL to Z. So yeah, 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 yeah. Yeah, yeah. So the action is completely classical. It's not corrected because, well, essentially it's impossible to write any corrections which would be holomorphic, because this is actually a very important requirement. The action of any isometry when it's lifted to twistor space, it must be holomorphic, and it's very non-trivial requirement, which essentially, yeah, makes everything well. At least the action is classical. Yeah. And this is what allows to actually apply SL to Z at the twistor level and find like all these instant on corrections, the instant on corrected mirror map. It's all just due to this holomorphicity.